two-phase and big M. Solve the linear program below using A, big M, and B, two-phase. Maximize z is equal to 2x sub 1 plus 3x sub 2 minus 5x sub 3. Subject to x sub 1 plus x sub 2 plus x sub 3 is equal to 7. 2x sub 1 minus 5x sub 2 plus x sub 3 is greater than or equal to 10, while x sub 1, x sub 2, and x sub 3 are all greater than or equal to 0. The linear program given has two constraints, one equality and one greater than or equal to inequality. The first step is to rewrite the equality constraint as two inequality constraints. Now we have three inequality constraints, two of which are greater than or equal to inequalities. We introduce the surplus variables s sub 1 and s sub 3 to the greater than or equal to inequalities, and the slack variable s sub 2 to the less than or equal to inequality. However, we need slack variables for each of our constraints in order to perform simple x and solve the linear program. From this point onwards, there are two methods which we can use to solve the linear program: big M and two-phase. Big M. Maximize z is equal to 2x sub 1 plus 3x sub 2 minus 5x sub 3 minus mr sub 1 minus mr sub 2. Subject to x sub 1 plus x sub 2 plus x sub 3 minus s sub n plus r sub 1 is equal to 7. X sub 1 plus x sub 2 plus x sub 3 plus x sub 2 is equal to 7. 2x sub 1 minus 5x sub 2 plus x sub 3 minus s sub 3 plus r sub 2 is equal to 10. While x sub 1, x sub 2, x sub 3, s sub 1, s sub 2, and s sub 3, as well as r sub 1 and r sub 2 are all greater than or equal to 0. By the big M method, we add artificial variables r sub 1 and r sub 2 to play the role of slack variables. But since these variables are not part of the original linear program, we need to penalize them in the objective function by assigning a very big number m, positive m for minimization problems and negative m for maximization problems, for their coefficient. This will force the artificial variables to take a value of 0 in the final solution. Now we construct our starting tableau with slack variables s sub 2, r sub 1, and r sub 2. Note that before we can begin iteration, the columns of the slack variables must be normalized. The columns of r sub 1 and r sub 2 are not initially normalized, so we must perform Gauss-Jordan row operations. Doing this, we now have our starting tableau. According to our optimality condition, we must select the basic variable in the objective function row with the most negative coefficient for maximization problems. Since m is treated as a very large number, we select x sub 1 with a coefficient of negative 2 to 3m as our entering variable. With the feasibility condition, we select r sub 2 as the leaving variable, performing simple x until the third iteration. We arrive at the optimal solution. Z is equal to 102 over 7, x sub 1 is equal to 45 over 7, x sub 2 is equal to 4 over 7, and the rest are all equal to 0. The two-phase method, on the other hand, solves the linear program in two phases. Phase 1 attempts to find a starting basic feasible solution, while Phase 2 solves the actual original problem, starting from the basic feasible solution obtained by Phase 1. In Phase 1, the artificial variables are introduced to the two greater than or equal to inequality constraints to play the role of slack variables. Regardless of whether the original problem is a maximization or minimization linear program, the objective function becomes the minimization of the sum of all artificial variables. In this case, it becomes min r sub 1 plus r sub 2. We then construct our starting tableau with our slack variables s sub 2, r sub 1, and r sub 2 as our basic variables. Notice that the columns of our basic variables for this iteration are not normalized. Gauss-Jordan row operations are needed before we can iterate. Once the tableau has been normalized, we apply the simple X algorithm. If we are left with a non-zero value for the sum of the artificial variables, we conclude that the linear program is infeasible. Note that the addition of artificial variables means that one of the original constraints was not satisfied. For this problem, both artificial variables are non-basic at the end of phase 1, and we have an objective function value of 0. We have found a starting basic feasible solution. X sub 1 is equal to 45 over 7, X sub 2 is equal to 4 over 7, X sub 3, S sub 1, S sub 2, and S sub 3 are all equal to 0. Since the artificial variables have already completed their task, we can drop them from the tableau completely and proceed with phase 2. We remove the columns of the artificial variables and bring back the original objective function into our tableau. Again, we see that the columns of our basic variables x sub 1, x sub 2, and s sub 2 are not normalized. After performing Gauss-Jordan row operations, we can now perform the simple X algorithm on the tableau. After just one more iteration, we arrive at the optimal solution . Z is equal to 102 over 7, X sub 1 is equal to 45 over 7, X sub 2 is equal to 4 over 7, while X sub 3, S sub 1, S sub 2, and S sub 3 are all equal to 0.